Should we go?
Hey, Steph, just don't forget to unmute. Green is good.
Okay, good afternoon, everyone. For those that don't know me, I'm Mike Pavlonis. I'm one of the 6 NOAA scientists stationed at the University of Wisconsin. And for the past 5 years, I've advised Stephanie Ortland, who is today's Colloquium speaker, on her research. So after completing her undergraduate degree in physics and earth science, Steph came to AOS in pursuit of a graduate degree in 2019, and she earned her master's in 2021. And today is very exciting because she's defending her PhD. And it's going to be, as you can see here, on convective nowcasting. Besides graduate research, she's very active in the AOS Graduate Student Association, as well as the local community as a mentor to middle school students. Professor Petty has served as Steph's academic advisor, and I think Grant will agree that Steph has been a pleasure to work with. And so very excited for her today. Just a quick logistical note before I hand it over to Steph. So Steph is going to present, then there will be a question and answer and discussion session. So please hold your questions till the end unless it's absolutely essential for clarification in the moment. So with that, Steph.
Hi everyone. Can everyone hear me okay in the back? Okay, awesome. Thanks Mike for the intro. I am here for my PhD defense today, so thank you all for coming. It's nice to see a full room. We're going to be talking about a model I built called ThunderCast throughout the presentation. Essentially it uses deep learning combined with satellite imagery and radar to make short-term forecasts. So we're going to start out this presentation by giving some background information about nowcasting and the specific observations we're using. After that, we're going to get to the 3 different sections of my dissertation. So to start off here, I mentioned the model I built is called ThunderCast. ThunderCast stands for the Thunderstorm Nowcasting Tool. And nowcasting refers to the fact that it's making short-term forecasts. Specifically, our model makes forecasts within the 0 to 1 hour time range. And we decided to build this model for 2 primary reasons. The first being that it can have some nice applications in the forecasting sector. We're hoping that it will be able to direct forecasters to areas that are likely to initiate into a thunderstorm, and do so by giving them additional lead time to hazards like lightning than they already have with existing models. The second reason goes to the science part of things. So we're building this model with our current understanding of observations and thunderstorms, so relationships between them two are being utilized here. And by doing that, where the model is not working as well, we're hopefully able to understand where perhaps our current understanding is lacking or needing some improvement. The 3 different observations we're going to be talking about for the duration of this talk, so I want to take some time to go through during the background section here, are satellite observations, radar reflectivity, and lightning. These are displayed on the bottom for a case study in Illinois where we get this nice, beautiful thunderstorm popping up and developing, growing into these mature clouds. So we'll talk about each of these different observations. The first one, satellite imagery. We're using the geostationary satellites from the GO satellites. Those have complete coverage across the United States. Since we're going for a forecast application for the US, this satellite works really well. Aboard the satellite is an imager called the Advanced Baseline Imager. This contains many different satellite bands. Specifically, there are bands that are used by forecasters to diagnose trends and patterns in cumulus clouds, such as cloud top glaciation. This is where you get ice at the top of the cloud, and then cloud top temperature can be observed with these satellite bands, as well as cloud morphology, so how the clouds are changing through time. An example of the satellite bands being used is the day cloud phase distinction, RGB. This is a false color, red, green, blue image. And since the bands physically relate to different processes, we can physically relate the colors here then to certain things in the clouds. So for example, a low, warm, water-based cloud is going to appear a blue color, a lighter blue color. As the cloud develops ice on the top of it, it's going to be called glaciating. That'll be a greener color. And then as the cloud develops into the upper levels of the atmosphere into the troposphere, in terms of a cumulus cloud, we're getting more ice at top. It's going to be really cold and have ice. Thin ice clouds can also have this property, and those would appear more of an orange color. In the context of a thunderstorm, we can think about what the thunderstorm life cycle would look like. We start with these cumulus clouds that are those light blue cyan colors. As we get further into the development, it gets that ice at the cloud top. We're getting that glaciation. Sometimes we're having some mixed phase particles with supercooled water as well as ice. That's going to start to appear, those green colors in the imagery. And then finally, the orange is going to be our mature phase where we're grown and you can see some of the overshooting tops at the cloud top. The next observation I'd like to talk about is radar reflectivity. Since field campaigns in the 1970s, the relationship between precipitation, radar echoes, and convective initiation of thunderstorms has been studied. When I say convective initiation here, I'm referring to the onset of deep moist convection. So specifically, I'm talking about that convection that we're associating with a thunderstorm. The National Hail Research Experiment, they found the relationship was between 30 and 40 dBz at about 10 degrees Celsius in the atmosphere is what they needed to then achieve or have something that would grow into a thunderstorm afterwards. So that's the range that they found in their field campaign. And this has fueled many different definitions of convection from a radar standpoint. So for this talk, we're going to refer to convective initiation of thunderstorms as our first indication of radar reflectivity reaching 30 dBz at negative 10 degrees Celsius. We went with the earliest end of, or the lowest end of that range because we're trying to get the earliest possible predictions that we can in the model. Other research experiments, they'll use 35 or sometimes 40, and these will kind of be referred to as a legacy-based definition because we're going back to some of the early field campaigns in the 70s to get this definition. The data set we're going to use for radar is multi-radar, multi-sensor. This is also referred to as MRMS. It's a suite of products, but we're specifically going to be grabbing the negative 10 degrees Celsius product. And if you are interested in more information about this, I have a couple of citations here on the screen. But when we go to what we're seeing for a thunderstorm, I want to point out here, I've engineered the color bar so that anything with MRMS radar reflectivity lower than our threshold for a thunderstorm is going to be a cool color, and then greater than our threshold is going to be a warm color. And so this will become important as we talk about the model development. Before we get to that though, I want to talk about the lightning observations. You'll see we're primarily going to be using this later in the presentation for evaluating how well our model is corresponding to thunderstorms. But the two different lightning observations we're going to be talking about are the satellite-based observation from the Geostationary Lightning Mapper. This is aboard the GO satellites. And then also Earth Networks Inc. or E&I. These are ground-based observations. So each of these has certain limitations associated with them, but combining both of them together will hopefully get a more robust look at all the lightning in the system. For example, from the GLM satellite standpoint, you're only observing what you can see from the top of the cloud. So by combining it with a ground-based instrument, we're hoping to get some of the lightning that it might be missing. Throughout the talk, you're going to see GLM as a flash extent density. This is in itself a number of flashes per amount of time, 5 minutes, and then per area. So you're going to see that as a pixel-based color on the right-hand side here. And then the E&I is going to be a point-based data. So you'll see that throughout the rest of the presentation. The last piece of background information before we get into my dissertation is on deep learning, because this is the process we're using to build the model. So deep learning itself is a form of machine learning, and it learns the rules to get from a set of inputs to a set of outputs. So in this case, we're trying to take our set of inputs, go through our deep learning model, and get a prediction of thunderstorms in the next hour, so a thunderstorm probability. Deep learning is really nice for computer vision tasks, and as we've seen from the previous observational slides, you can get a nice visual look at what some of these patterns are, especially in the satellite imagery. So deep learning is set up really nicely to be able to use satellite imagery, and it's been shown to do this well for other applications in our field. To train the model to learn the rules to get from our set of inputs to our outputs, our predictions, we need to compare them to a target data set for many, many different case studies or different examples. Once we want our predictions to be as close to the targets as they can get, and we do that by measuring the difference between them using a loss function, and then we optimize the model. So the deep learning model itself has many different layers inside of it. Those layers are each associated with a data transformation, and then it has a weight to characterize how important that layer is to get from our inputs to our outputs. So we can change the weights to say maybe one layer is more important than another layer, and do that until our predictions get as close to our targets as possible. That's called optimizing the model. After we are satisfied with that, we're doing some validation and some testing. We're not going to talk a lot about that for the rest of the presentation, but those would be the stages to get a deep learning model that would then be able to go directly from its inputs to its predictions. So this would be the final product. We wouldn't need the training set afterwards. Okay, so that brings us to my dissertation. I know 11 minutes in of background, that can be a lot to take in, but it's necessary to kind of understand where I'm going with this for the rest of the dissertation. So I've split the dissertation into 3 different sections. The first is the development and the initial performance of the model, so ThunderCast development here. And then after that, as I mentioned, we can learn a lot about what a model's doing and where our science is maybe limited by looking at some of the model limitations. So the second section, we're trying to look for influences on the reliability and applicability of the model to thunderstorm nowcasting. And then the last section, we're specifically going to look at some of those limitations associated with using satellite imagery. For each of these sections, we're going to go through a guiding research question, a summary of the methods we're using, and then really focus on some of the key findings for each section. So the first research question, again, this is the section where we're looking at the initial performance and the development of ThunderCast. So we're really focused on how well can we predict the occurrence of convection in the next hour, specifically using deep learning and our scientific understanding of satellite imagery and radar observations. We're going to kind of give an overall summary of this, but I wanted to mention that this part of my dissertation has been published, so if you're interested in going into a lot of the details and the methods, I would recommend checking out my paper listed on the screen here. Okay, so for ThunderCast development, if we go back to our AI development diagram here, we can put it in the context of our model. So first, if we take a look at the inputs, I've now filled this in. So we're using our satellite imagery here. It gives us a full look at the United States, including areas where perhaps we don't have radar coverage. So this sets it up really nicely, especially since it's a very visual image. The specific bands we're using are 0.6 micron, that's a visible channel. Then we have 1.6 micron, that's commonly known as the snow ice band. And then we have 10.3 micron and 12.3 micron. Those are infrared channels and that are commonly referred to as the long-wave window and the dirty long-wave window bands. The model we're using is a UNet convolutional neural network. There are tons of different AI models out there. We chose this one because it allows us to learn both small-scale and large-scale patterns, and it also works well for a segmentation project. which essentially means we're making pixel by pixel identification or probabilities at the end instead of a full image characterization. And then throughout the deep learning process, the model, it starts as an image that you would normally see. It goes through its convolutions, and then at the end, it's back at the same size. So this works really well for getting a product out for forecasting. The targets we're going to be using, this goes back to our radar definition of convection that we had talked about in our background section. So here, anything greater than 30 dBz is going to be considered a thunderstorm. Anything less than that, we're going to consider not to be a thunderstorm, so a yes-no thunderstorm case. Except instead of using an instantaneous radar for that specific timestamp, we're going to need some information into the future to get a prediction. We're doing that by taking the maximum radar reflectivity to an hour in the future from the current timestamp. And then that threshold from the radar perspective is applied to the maximum radar reflectivity. This gives us some information about time without actually introducing time as a variable into the model. You might be asking yourself, why are we not using lightning? Because if we're trying to make a prediction for a thunderstorm, a lightning is what you really need to be considered a thunderstorm, so why not use lightning? Well, first, that's already been done. My colleague John Centennial and Lena are working on this project right now called Nowcasting. That's what this does. It makes predictions off of GLM. But also, if we think about the life cycle of a thunderstorm, initially here on the left-hand side, at the beginning of the life cycle, you get some cumulus clouds developing. You see that first in the satellite imagery. As time goes on, you then get a radar reflectivity signature corresponding to our 30 dBz threshold, and after that, we'll see lightning. So the thought is, if we can target something that's happening earlier in the life cycle process, then perhaps we can get increased lead times to hazards than a model could if it's predicting things just on lightning alone. So this is why we've chosen to use radar reflectivity here instead of lightning. Before we get to the performance part of the talk, I wanted to take a brief moment to go over some important terms that are going to be used throughout the remaining part of the talk. So here we have the terms on the right-hand side: true positive, false positive, true negative, false negative. Essentially, the positive or negative part of these terms refer to, do you have a prediction or don't you have a prediction? So positive, prediction; negative, there was not a prediction from ThunderCast. The true or false refer to, did we meet our target data set? So did we meet the 30 dBz at negative 10 degrees Celsius, or did we not? So true, yes, we did; false, no, we didn't. So this is going to be important going forward. And for example, false positive, this is where you have a prediction, but you don't actually meet 30 dBz, so that would be a false alarm. All right, so now let's switch gears and see how ThunderCast is doing overall. We have some really nice case studies coming out of this where ThunderCast is able to identify 30 dBz and give us lead time to hazards. So here you're seeing the advanced baseline imager visible band in the background. And then we have our radar reflectivity layered on top of that with our color bar as I described, so that 30 dBz is going to be the warmer colors or greater. And then lastly, ThunderCast's probability or its predictions are going to be these contour colored. So the lighter the contour, the lower the probability is. So here on the first panel, we don't have any radar yet, but we can see a little bit of bright colors in the visible band, and then you can see that ThunderCast is able to identify this region as having the potential to have a thunderstorm. As time goes on, those predictions become larger in probability, and then finally, 25 minutes after our initial predictions, you're seeing that 30 dBz signature. So 25 minutes to 30 dBz, and then lightning happens 50 minutes after our original prediction. So we're getting a lot of lead time here to that lightning hazard. So overall, from case studies, we're seeing that ThunderCast performs really well to get us to that 30 dBz mark. And If we look at the overall statistics instead of just the case study, we see that yes, we are performing really well for accuracy, recall, and specificity. However, we are seeing some really low values of precision. So what precision is here is on the bottom of the screen, you'll see it's the number of true positives over our total number of predictions. So if you have a low precision, that means that you have a lot of false alarms. So the model is really prone to false positive predictions or false alarms. And we do see some slight reduction in our performance at night. But overall, ThunderCast is successfully identifying cases with 30 dBz. We're able to go from our satellite images through our deep learning model to get an indication of thunderstorms in the next hour. We're just seeing some enhanced false alarms here. So we might be asking ourselves then, where and why is this happening? Can we improve this in the future iteration of the model? So what's going on? What's causing some of these issues? You might be tempted to say, well, maybe we can look at this box and see what are the rules that the model's learning, but this is a very active area of research in artificial intelligence and machine learning right now. It can often lead to more questions than answers, so we're going to hopefully close that box. And instead, we're going to acknowledge that our model is only as good as the data and the definitions that we're using to create the model. And in doing so, we can maybe think about, okay, so we're using satellite imagery. What does the satellite imagery look like for these false positive cases? Are there clouds? Are there no clouds? What types of clouds are they? Are they convective? Are they stratiform? Are there no clouds at all? That's also a problem. So if we can figure out maybe what cases this is happening in, we can maybe identify a route forward to improving the false alarms. Also, we're using a definition from radar reflectivity for a thunderstorm. Naturally, this is going to be imperfect. We're going to have cases that perhaps make 30 dBz but don't actually produce lightning. So our question is how often this is happening? Is it widespread? Is it not? It doesn't necessarily mean that ThunderCast is not useful if it's happening, but it does mean that it could impact if a forecaster, for example, is specifically relying on it for thunderstorm detection, that this would have to be something that they would need to keep in mind. So we're interested in figuring out what's going on with the data, what's going on with our definitions here, perhaps identifying an avenue forward to help improve the model. So this leads us to a second research question. What are factors are impacting how reliable and applicable the model is for thunderstorm prediction? And we're going to evaluate this by looking at many, many different areas of predictions. So specifically, we're able to grab information such as radar information and satellite information for a lot of different cases. But it can be really hard to do that because identifying a case manually can take a lot of time. For a statistical analysis, we need a lot of cases in order to get some useful information out of it. So to get a lot of cases, we're using an automatic method where we're identifying objects. What I mean by that is if we have the ThunderCast predictions, we have regions inside of it, like these bright white areas, that are high predictions. And if we were able to grab that region with an object tracker, then we could then get information for it. So we could do that for this one as well as the areas around it and then track them through time and do this in a way where we don't have to be manually identifying each case. So the cases we're collecting, I just wanted to briefly mention, they're from the convective season in 2022, and we're doing this for randomly selected days in each month of that season. We're going to collect the objects using an object tracker that's already established. It's called TOBAC. TOBAC was originally designed to track and analyze clouds. However, it is what we call input variable agnostic, which means that you don't have to use the same data set that they use to go through the TOBAC to get an object out. You can use whatever input you want and it will still identify objects. So, for example, if we were to give tow back some data that maybe look like this, where our lighter colors are our lighter probabilities, our darker colors are perhaps our darker or our higher probabilities. We put it into towback. What towback's going to do is it's going to identify points of interest. Those points are what we're going to call features, and they're the black plus signs here. And then after it identifies features, it uses a watershed algorithm to get the areas around the feature points that relate to the point itself. So that's how we're getting our objects. After we get the objects, we're able to track them through time. And then we're going to gather data and then sort them based on the data we're gathering for them. So for example, we can say, did they meet 30 dBz, did they not, did they have lightning, or didn't they? So for example here, this is our same ThunderCast predictions from a couple slides ago. This is what towback is able to identify in terms of objects, and then we can layer on top of them our radar reflectivities and our lightning from GLM and ENI, so our satellite and our ground-based lightning detection systems. After we've gone through all these methods, this is our results. We had over 24,000 cases that we were able to grab with our object tracker. And if we look first at this part of the graph, this is the amount of true positives and false positives we were able to identify. So 32.2% of the cases were false positives. So when I'm talking about the cases, that's a predictive storm trap. So it's something that ThunderCast has predicted, and we're tracking it through time. So interestingly, we see the false positives coming through in our first section of the table, and it's kind of confirming what we found in the previous statistics, but also when we split the data set based on lightning or no lightning, we find this interesting number coming out where 40.2% of the traps were true positive that didn't have lightning. So that means over half of our true positive cases did not actually correspond to a lightning event. So this could be a problem if you're relying on ThunderCast to identify only thunderstorms. And it indicates that our definition from a radar's perspective, so our MRMS radar reflectivity threshold of 30 dBz, it's not as well correlated to lightning initiation as we thought from previous research.
Is there a lag involved? Sorry, it's lightning at the same time or lightning later?
Lightning within an hour.
Okay,
Yeah.
thank you.
Okay, so we wanted to see how widespread this issue is. Is it widespread in terms of time or spatially? So here's a graph of the number of predictive storm tracks on the y-axis versus the month. And we can see, yes, we're identifying there's true positives with and without lightning cases scattered through all the months we're looking at. However, I wanted to point out here that April actually contains more false positives than true positives, whereas the rest of the months contain more true positives overall than false positives. We are speculating that this has to do with the characterization of April. Well, April is characterized by the transition from spring to summer. So naturally, it's going to have more mid-latitude cyclone events that perhaps generate more types of clouds and more precipitation modes. So perhaps this is an indication that our 30 dBz threshold is not quite filtering out all of the cases in that respect. So maybe we're getting some cloud types here that don't correspond to convective activity. In terms of spatially, we have our different regions of the U.S. marked by the graph here on the left-hand side. So for each region, we're seeing that we have true positives, we have false positives, but we also have cases that do not actually have lightning, and this is happening kind of across all the regions of the United States. However, I'd like to point out an interesting point of this graph, and this is that if you look at all of these regions, we have a smaller orange region, so that means we have less cases that have lightning than don't have lightning, which is the blue region, except for the Southwest. So this is really interesting because during the 2022 convective season, the Southwest was really impacted by the North American monsoon system. The monsoon, it transports moisture from Pacific Ocean and the Gulfs to a normally dry region, and this fuels thunderstorm development. And there's something be about having this extra moisture come into a normally dry region that fuels more thunderstorms than it doesn't fuel thunderstorms. That's something that we're considering and could be an avenue for future work to kind of figure out why maybe this region of the United States has this pattern. So we've talked about the 30 dBz threshold and how we haven't quite, it seems like that threshold is not quite doing what we want it to with identifying and filtering out different cases. So we wanted to take a look at, does the 30 dBz matter in the sense, could we shift the number? Could 35 or 40, based on the previous field campaigns, make a difference here? Could that help us filter out some of the cases we're seeing? So here we have our maximum radar reflectivity. This is for our predictive storm objects, and then this number of predictive storms in those different buckets of radar reflectivity on the y-axis. If we start with the false positive side of things, we see that the closer we get to 30 dBz, the more cases we have, and we took a closer look at some of these cases, and yes, we do see some stratiform structures in these false positive cases, so our 30 dBz is not quite filtering out all these cases like we would have hoped it would. Also, we see some zero reflectivity cases, so there's some predictions in areas that don't have any clouds at all, and we took a closer look at that, and typically they happen over high contrast physical features. This is something that could be fixed in a future iteration by giving the model more examples of those high contrast cases in the training data set. If we look at the other side of the graph, we do see the peak of the cases without lightning that do hit 30 dBz occurs at a higher maximum radar. However, they still overlap with cases that do not have lightning. And we actually see true positive cases, so cases that hit 30 dBz that don't have lightning happening at very high reflectivities here. There's some at over 50, over 45 dBz. So this indicates that moving that radar threshold is not necessarily going to fix all of the problems that we're seeing. There's been some previous research that's looked at area instead of just the dBz threshold, so perhaps incorporating area as a predictor could help improve the model. Well, we took a closer look at this, where we're seeing, okay, the number of tracks again on the y-axis, and then each of these graphs is the area or number of pixels in an image that meet a certain threshold. So here we have 30 dBz, 35, 40, and 45. If we look at the 30 dBz graph, yes, our cases with lightning are shifted to higher areas with the peak of that, those cases. However, they still very much, again, overlap with the cases that don't have lightning. As we get to these higher thresholds of radar reflectivity, they are even more aligned. So incorporating area here would not necessarily help either. So this indicates that areas of reflectivity are not able to differentiate between our cases with and without lightning. So we've talked a lot about the radar. What about the satellite perspective? So here we're going to be looking at the brightness temperature from the cloud top and the maximum radar at negative 10 degrees Celsius on the x-axis. And what's really interesting about this is we can look at our true positives with and without lightning. So the top are the cases that are true positives, so those are cases that do hit 30 dBz. The bottom two graphs are the cases that don't hit 30 dBz, they're false positive. And then the right-hand side, those are our cases without lightning. And our left-hand side are the cases with lightning. To understand what this graph is showing with us, I'd like to think of it in terms of what would a thunderstorm look like on this graph. And from a cloud top temperature perspective, we would expect to see a very cold cloud top. We'd expect to see a case that's lower than our melting temperature, in most cases much lower than our melting temperature, because if you're right around the melting temperature, that means you could have some super cooled water in the cloud as well as just ice at the top of the cloud. So it's interesting then, if we would expect to have cold temperatures that are false positive cases without lightning and are true positive cases without lightning, they do have some warm cases. So we took a closer look at those and we found that oftentimes these warmer cases are actually a result of the resolution of the images instead of the actual temperatures of the cloud. So for example, in the visible, you can see a nice cumulus cloud developing, but it's really small. So the visible, that's a 0.5 kilometer resolution. The IR band, where we're getting our cloud type temperature from, that's a 2 kilometer resolution. So it's much coarser and those pixels tend to get blended out with areas around it. Okay, so if we look at these regions of high predictions, we can see that the mean of our cases with lightning that do hit 30 dBz is colder than the surrounding cases. So that's what you would expect. However, if you look at the concentrations of our cases without lightning, these concentrations overlap with cases that have lightning. So this is really important because it's indicating that regardless of the presence of lightning or radar reflectivity, we're achieving cloud top glaciation, which is necessary for lightning formation. So likely we'll have ice and or a combination of supercooled water at cloud top. We wanted to take a step further and we wanted to look at the 1.6 micron reflectance band. This is the snow ice band. And what's interesting about the snow ice band is ice is strongly absorbing at low reflectances. So the cloud tops likely contain ice when you have low reflectances. And if you look at the mean where all of these high concentrations are for each of these graphs, they're all concentrated at these lower reflectance values. So this indicates that cases likely look similar from a satellite perspective, regardless of whether they hit 30 dBz or if they have lightning or not. So this is a very interesting thing coming out of this analysis. We wanted to take a closer look at it. We wanted to see what do those cases actually look like from a satellite perspective. Can we identify those signatures that we were suggesting that they might actually look really similar? So we're going to take a look at 4 different case studies here. We're going to look at Oklahoma, Texas, Alaska, and Tennessee. And so that gives us a wide variety of cases through the United States. Before we do that, I just wanted to remind you of what the RGB image looks like for a thunderstorm. You're going to start with those cyan, light blue colors, and then as you develop into the storm, you're going to get glaciated. You're going to get that ice at the cloud top. That'll appear those green colors. And then finally, you'll start to see the orange colors as the thunderstorm starts to mature. So for our first case study, this is in Oklahoma. Here we're looking in May, and what's unique about this case study is this is a severe weather day. What I mean by that is forecasters are looking at this area as a potential for severe weather, and some of the key ingredients that they can see, like CAPE and wind shear, so convective available potential energy and wind shear, they're really favorable for a severe weather environment. We have lots of instability and we have high wind shear. Now, I wanted to mention you do not need high CAPE and high wind shear to produce a thunderstorm. But if you have these things, it's more likely that you'll be able to sustain a thunderstorm, especially this is what you would expect to see for a supercell environment. If we look on the left-hand side of the screen, these are our RGB images. We see a lot of activity at the lower part of the RGB, but we want to actually focus a little bit farther up. So if we look at where this arrow is pointing, there's 2 storms that start to develop. One of them produces lightning and one of them doesn't, and both of them hit 30 dBz. So let's take a closer look at them. So here we have them side by side, but let's look at the leftmost case to start with. We can see a lot of these green colors. That's indicating our glaciation. As it develops further, you're starting to see these vertical growth signatures of those orange colors. However, this is the storm that does not produce lightning. So after this, the storm dissipates. If we look at the other storm, these are a little bit farther apart, but you still see some of these glaciation colors. As the storm develops further, you get those nice oranges. You can see a little bit of an overshooting top here, and you do get lightning actually at this last time step in this series of images. If we put those side by side, both of them look really similar. You get the same colors, they are about the same size, they're in the same environment, happening around the same time. So this is, to me, indicating that initiating non-electrified storms, they do appear similar in the satellite imagery to initiating thunderstorms, and this kind of confirms what our object-based analysis was suggesting to us. Also, I mentioned this is a severe weather day, and a lot of the information that forecasters have widely available across the United States, like convective available potential energy, wind shear, and convective inhibition, are showing that this is likely to have storms, and these then would not be sufficient to tell the difference between the two, because we did not see a difference in these values for this area. We'll switch gears a little bit. This is a completely different sort of thunderstorm environment. This is sea breeze convection. So what's happening in a sea breeze convection is it's forced, where we're getting relatively cold air over the Gulf of Mexico here, and this is forcing, it's pushing itself onto land, so that air is going from the Gulf to the land, and the land is relatively warm. So the warm air then is going to be forced to rise, and you can get a lot of development off the coast of these types of storms. So if we look at the satellite imagery, as the day starts to progress, you do get a lot of storms firing up. Some of them quickly die, a lot of them hit 30 dBz, and some produce lightning and some don't. So this is where we can kind of play a game. Storm 1 and Storm 2, both of these are in the scene, and one of them produces lightning and one of them doesn't. And I challenge you to tell me which one produces lightning and which one does not. Both of them have our green colors for glaciating cumulus, and you get a little bit of yellows at the last timestamps. Whoop. Okay, and now that we've told you the answer, it is the second one that produces lightning, but if you look at the last timestamp, this really looks similar to the timestamp above it. The two storms look so similar, and it's not as orange as the other case study that we looked at, so you don't necessarily need to get that orange color to produce these lightning signatures. So what this tells us is these sorts of patterns are happening not only in one specific meteorology environment, but they're happening in other types of environments as well. This can also happen at high latitudes. This is a case from Alaska. This is an above average temperature day, and we had a lot of development across the interiors of Alaska on this July 27th date. And both of these storms, again, Storm 1, Storm 2, can you tell me which one produces lightning? I probably would not be able to tell you, but I already know the answer is Storm 1. So this is the one that produces lightning in this case. And actually, to me, this looks maybe less developed than this one is. It's a lot smaller. Okay, so this can happen across a wide range of meteorology conditions as well as a wide range of latitudes. The last case is different. So the cases we've looked at, they're quick developing convection cases. This is convection across Tennessee. And what's really interesting about this, you can see the RGB image. We have a lot of cumulus clouds kind of congregating together, and so they're really well organized, and they're traveling to the southwest. They get that glaciation color, and they do hit 30 dBz, but they don't produce lightning. So there's no storms right here that do produce lightning. So this is just a case that doesn't produce lightning. And then our CAPE values, there's a moderate instability, there's a lot of precipitable water and high humidity, weak wind shear, so we wouldn't expect it to sustain a storm, but it could produce one. You still don't need a really high wind shear to actually have a storm. If we look at these individual slides of the RGB video, we can see that we actually hit a maximum reflectivity of 51 dBz. So this is definitely an indication that our definition from a radar perspective is not doing what we'd like, because this case looks exactly like we'd expect a thunderstorm to look like. It's got the glaciation, you're getting a little bit of oranges, and we're hitting a maximum reflectivity that's really large. It's also present for a long time, so it's not just a quick developing thing. To me, this is reminiscent of a tropical type structure. We're getting really large reflectivities, it's long lasting, but it doesn't produce lightning, and that can happen in the tropics. So the tropics, this is usually due to high entrainment of air, resulting in weak updrafts. So we could speculate here that maybe something like that is happening here in the latitudes. And this indicates then that convection with tropical characteristics, it can occur in the mid-latitudes. It's not as distinguished as tropical and mid-latitude. There is some overlap there. And this could then contribute to false alarm cases. So this is something we need to improve on for a thunderstorm case. However, this storm did produce a lot of rain, so it could still be useful for identifying that. Yes, so tropical convection cases can happen in the mid-latitudes, and also an avenue for future work would be to see how widespread this is happening, and does it increase with a changing climate? As we're seeing more warm temperatures, is this something that we're going to have to take into account more often in the future? So overall, that was a lot of information for my dissertation. We've gone over the development, the performance of ThunderCast, which makes near-term forecasts for convective activity associated with thunderstorms. It does really well from a 30 dBz standpoint, but we wanted to look at some limitations. So let's take a look at our overall summary, just to remind you of everything we've gone over. So ThunderCast does well in terms of accuracy, recall, and specificity, but it does have some false alarms. So we identify cases with 30 dBz, but there are some cases that we are seeing that don't actually correspond to that. So in doing so, we then decided to take a look at the limitations a little bit closer, and we found that over half of our true positive cases, they did not actually correspond to lightning, and this indicates a distinct reflectivity threshold. Separating tracks is not present or not clearly identifiable, and also our true positive tracks with and without lightning, they likely contain cloud top signatures that are similar, so the tracks likely appear similar in our satellite imagery. Lastly, we took a closer look at the satellite imagery, and we found that this similar pattern in the satellite imagery for initiating and thunderstorms and non-electrified storms. This can happen in a wide variety of meteorology environments, it can happen at a wide range of latitudes, and it indicates that known generalizable precursors for thunderstorm initiation from a remote sensing standpoint and a ground-based observational standpoint are not quite able to provide enough information to determine whether we will grow into a mature cumuli or cumulonimbus, or if it'll stay kind of a regular cumulus type structure. This is really limiting for artificial intelligence. So I wanted to take a second here just to mention we're building the model based on satellite imagery. And if we can't see the difference from a human standpoint in the satellite imagery, then the model's gonna have a hard time learning those patterns. So this indicates that we would probably need some sort of other predictor to fix this problem. Okay, so with that, I'd like to say thank you. There's so many people I want to thank. I'm not going to go through everybody on this list, but I really wanted to say thank you to Mike and Grant especially, as well as my committee, my friends and colleagues here at UW, and Liz Maroon's my writing group, which kept me on track to finish my dissertation on time, and my family for being there to support me. And lastly, I wanted to mention that I'm going to be starting a postdoc at CIRA in December. So thank you to Jason Apke and Renate for setting that up for me. So thank you, everyone. Happy to take some questions now. Also some water. Yes.
Maybe students, yeah, usually we
Oh,
let
sorry
students
about
go
that.
first. Sorry, my fault.
Yes.
So I don't know too much about like the predictive like machine learning, but to my base knowledge, I kind of divide it into like two separate groups of like, I guess like almost like binary prediction of being able to predict, is there thunderstorm or is there not thunderstorm?
Mm-hmm.
And then kind of like graded, like saying like, I predict like heavy thunderstorm versus like medium thunderstorm, like a storm with no lightning, storm with lightning. I guess my question is, how different are those two ideas, and like, do you think you have somewhat of a basis for being able to maybe make or use machine learning to like kind of have graded estimates of thunderstorms and stuff like that?
Sure, so what I'm doing right now is more of a binary, is there activity, is there not, and then we're taking the output and putting it on a scale between 0 and 1, so that's where we're getting our probability kind of value out. But what you could do is you could use a multiple class model where you would say, perhaps these are your cases that have lightning, these are your cases that are really severe, and try to have the model identify that. But you would have to have, the trick is, you'd have to have a data set that matches that. And it could take a lot of time for a manual evaluation and the manual kind of, these are the ones that are severe, these are the ones that aren't, these are perhaps the ones that produce rain and not any lightning. So I think there's an avenue that you could explore to do a multiple class kind of evaluation with a deep learning model, but it would definitely take some thinking about the best way to do that from the target standpoint. So I think your target would be your limit there. Other questions? Yeah, Ian?
Great talk, this is wonderful. This is a two-parter. The first being, does your model use the context of previous time steps as an input? And then the second part of that would be, if that is the case, do you find better skill when you look at mesoscale sectors versus CONUS or full disk views?
So right now it does not. There are deep learning models out there or other machine learning techniques that do incorporate time, and that's something that I've thought about doing, but because I needed to focus on kind of more the science side of things and not necessarily just the development, we did move on and focus just with our deep learning UNet. But it is something I'd like to explore in the future and is potentially an avenue I can go for in my postdoc. Becca, you have a question?
Does your model, the ones you included in your case studies, were they all like over land-based? Was it computer or land versus like ocean?
So they were primarily focused over land. However, we did include cases right along the coastline. So because we're using radar, we're limited to where we have radar coverage for our target data set. So we were able to get some like right along the coast, but we didn't actually have an ocean-based category. Yeah, Clark?
So I know that you were just basically saying if it was true or false based on if there was a thunderstorm within that hour, right? Did you test to see if like any of those false positives had a thunderstorm maybe later than that hour?
Yeah. So we looked, so when we're, the initial true positive or false positive is, did it happen within the next hour, because that's what the target is, and then when we did our object-based analysis, it was for the duration of the object. So the object could, if it was existing for longer than an hour, we did include those types of lightning. And then we did make sure we were collecting information for each of those predictive storm objects until we hit 30 dBz and we had lightning if it was going to be present. Yeah. Other questions? Larissa?
Yeah. So one of the things when you have some entrainment in a storm, one of the things that really influences how fast your updraft velocities get is environmental humidity. And so I'm just wondering if that's reflected in any of the satellite data that you're looking at, or if that would be like something that you could use to try and distinguish like why some of these are developing lightning and some aren't. Or
Yeah, that's definitely something I've thought about and will hopefully do some experimenting with, but there is a water vapor channel in the AVI bands that we could try to incorporate. I'm not 100% sure about the logistics, but I think there is an avenue there to kind of go forward. I've also seen some people using numerical weather predictions in sort of a predictor. However, that kind of, it's prediction, it's not an observations, but you could see if that might improve it. And I think they have some information there about water content too. Yeah.
so right now there's no. But
Right now there's not, but we could go look at doing that in the future. Yeah. Cool. Scott.
This is kind of a speculative question, but
Okay.
there are lots of other machine learning tools, and I'm thinking especially of Gremlin,
Yes.
which is a radar estimator, and it takes AVI data and GLM data.
Yeah, that's
trained
kind of
against
Hilbert's
radar.
model. Yeah.
Right. So I'm kind of curious, if you had like a scatter plot with ThunderCast on one axis and Gremlin on the other. Could that inform you anything about storm structure, or is the information that's kind of lost in the machine learning black box, is it going to obscure things?
I think you'd have to be really careful with your analysis there. I don't know exactly. I would have to do some experimenting, I think, with that one. But for sure, if you looked at cases where Gremlin maybe isn't doing as well, maybe you could compare it to cases that ThunderCast isn't doing as well on and see if they're very similar, especially if they're both using satellite imagery. Because that satellite imagery is going to be a limiting factor no matter where you're looking at convective initiation. I mean, so many models that looked at convective initiation in the past 10 years, for example, they all have this issue with false alarms. And so that's where this came in. We were like, okay, well, maybe we should actually look at what's causing them instead of just using a different model type. So I think you could get some good information. I know I'm straying from your question a little bit, maybe because I'm not 100% sure what to
Gremlin is just
answer
telling
it,
you,
but
is there rain or not versus
Right.
is there going to be lightning? So I'm kind of curious how it would separate out the two different rain modes, convective versus non-convective.
yeah, I think that would be interesting to see.
Even though Gremlin is much better when there's GLM observations.
Yeah, I'll keep that in mind for the future, Scott. Thank you. Brad?
So ABI is able to see cloud top glaciation, but you don't really know how deep that glaciated layer is. How much does the depth of that glaciation and not knowing that contribute to your false?
I think that could definitely be a factor. I mean, we're limited by the cloud top here. We can
Right.
only see what's at the cloud top. I don't know how to fix that exactly. I'd have to do some diving and to see if there's another sort of data set we could use. But yeah, I think it's definitely a factor because the initiation theories for for lightning initiation, they depend on, do you have grapple and do you have this super cool water that's kind of creating these rhymed particles, and then they have to be colliding and they have to be distributing the charge that way. So I think it's not necessarily do you just have ice at the cloud top, but how widespread is that? Do you have these particles that are actually flowing in the updraft? So yeah, I think there's some merit there. I'm not 100% sure how to approach getting some more information.
Would
Yeah.
CloudSat help with that?
So CloudSat, I believe it doesn't, correct me if I'm wrong here, but CloudSat doesn't have like the 5-minute intervals, right?
Or you definitely
Yeah.
only deal with cases
Yeah,
with
so
CloudSat and Zoom.
I think that would be kind of limiting because when you're looking at the thunderstorms that rapidly develop
Right.
and then kind of trying to track them around, you'd only be able to get a certain area of the United States. You might be missing other areas, and then you wouldn't have kind of the temporal.
Right, you wouldn't be
Yeah.
able to do full set.
Yeah, so I think that's the limit there. Becca, do you have another question?
Yeah, in the object ID, was anything about preset threshold, like set for like how much, like once it's been connected to another, like defining those two separate objects?
Could you repeat it? Sorry, it's kind of hard to hear up here.
Yeah, so in like ID of objects,
Mhm.
is there like a preset threshold set for those, like to differentiate objects from one another?
No, there wasn't any precipitation threshold because the objects are made just on the ThunderCast predictions. So they're only incorporating, what's the area of the prediction? And then when we're layering it on top of other data sets, I did not use a rainfall one, though we did look at the specific case studies. I did pull some rainfall data just to verify that, yeah, there's a storm there and it's producing some precipitation. That's like the Tennessee case. There was a lot of precipitation that day. We just didn't get any of the lightning. Other questions? Pete, do you have somebody online?
There's 2 questions online, one from Jason Epke. He asks, does ThunderCast show any promise at resolving ongoing thunderstorms, 30 dBz echoes that decay, versus identifying where storms initiate?
Right. So we have not done a lot of work on the decay stage yet, but we're hoping to dive into that more. I mean, especially since a lot of these initiating storms, they seem to decay a lot faster if they don't have lightning than the ones that don't, except for perhaps a tropical type case. So I would say I haven't done that yet, but I'm hoping to do that more, and Jason knows that because he's going to be working with me in the future.
Okay, there's one other one from No Chen. She first gave you some claps, and then she said, would adding satellite images and other channels that monitor chemical tracers improve the true positives?
Chemical tracers, that's interesting. Yeah, so chemical tracers can be important for cloud growth, for your cloud nuclei development. I haven't thought a lot about what that would look like, but I could experiment with it. I'll make a note down, but I don't know exactly the answer to it yet because I haven't done it. David?
So your definition of CI kind of stems from an old definition back in our radio network, was just regular radar. Now we've advanced to more local methods. Do you think adding information such as particle shape or fuzzy logic to better train would be useful?
I think it could be useful, especially if you get some information about different particle sizes, because that could lead to some more information about the lightning initiation side of things. I think the trick is, though, that the Dopplers, you have to make sure that you have a data set that's widely applicable across the United States, because you don't want to just kind of pick and choose certain areas, because then if you don't represent one area and if the convection looks slightly different in that specific area, then that won't be included in the model. So I think we'd have to verify that the Doppler information that we were able to get about particle size, et cetera, would be able to be applied across the United States. Okay, other questions? All right, I want to say thank you to everyone again for coming and being part of this experience with me. So thanks, everyone.
So at this point, we're going to be going into the private part of the defense for Stephanie. But before all of you, or most of you, go away, I wanted to mention again, for those who might not have gotten the information, that we're having a reception at our house at 7 o'clock in observance of her defense today. And if you'd like to come and you don't have the address already, it might be on a flyer somewhere. I'm not sure where. So there's a flyer in the lobby, right? That has.
There's one right by the elevator.
Right by the elevator, so you can look at the address there, and anybody's welcome to come to help us celebrate this event. So thank you very much.